Hi, welcome to this video on alkanes. To start off with, what are alkanes? So alkanes are the simplest family of hydrocarbons, and hydrocarbons are compounds that contain carbon and hydrogen only. First thing we need to know about alkanes is the general formula, which is CnH2n plus 2. Alkanes are saturated, and this is because they have only single carbon-to-carbon bonds, so you cannot add any more hydrogen to that. Let's look at naming and drawing alkanes. So the first way of representing alkanes is by using a molecular formula, whereby you count the number of each atom in the molecule. So for example, for methane, we would count how many carbons there are and how many hydrogens there are. So in this case, we've got 1 carbon and 4 hydrogens. But this doesn't allow you to see how the atoms are joined together. So therefore, we can use a displayed formula, which shows all the bonds in the molecule. And just remember that a single line represents a pair of shared electrons. So here, we have a displayed formula of methane, whereby we can see that carbon is attached to the 4 hydrogens, and as I said, the single line represents that the hydrogen and the carbon are sharing a pair of electrons. We also have a simplified displayed formula. So for the simplified displayed formula, for example, if we were to consider ethane, which has 2 carbons and 6 hydrogens, we would write it as CH3, CH3. That would be the simplified displayed formula. The skeletal formula is where all the hydrogen atoms are removed from the carbon chain, leaving just the carbon skeleton. And we also display any functional groups, which we'll encounter later on. So for example, if you were to draw propane, which is has 3 carbons, we would draw it like this. So then we can see that the end of each line represents a carbon. So we could also, just to explain, we could show it that there's a carbon here, and a carbon here. But as you can see, we wouldn't normally draw the carbons in, we would just draw the lines. So this is just to explain where the carbons are. So that shows that we've got propane. The single line represents a single bond, and if you wanted to see where the carbons would go, sorry, the hydrogens would go, you could see it as that. But as I mentioned, we would only draw the carbon chain without the hydrogens attached. These are the different ways you can draw alkanes and other organic compounds, but we'll discuss that at a later date. How do we name alkanes? So first of all, we look for the longest carbon chain. So for example, in propane, we look at how many carbons there are in the chain. We've got 1, 2, 3. And the 3 will be representing it by prop, which will be the prefix of the name, which is prop here. And by using ane on the end, we know that it's an alkane, meaning that there is only single carbon bonds. So we can use the same for if we have 1 carbon, we would use meth in the beginning and ane in the end to show that there's only single bonds. So in this case we've got methane, ethane, propane and butane. So for butane, again, we count the number of carbons, so it's 1, 2, 3, 4. Therefore it is bute, and because there's only single bonds here, we add ane on the end. Let's consider isomerism. Isomerism is when a molecule or molecules have the same molecular formula but have a different arrangement of the atoms in space. but that excludes any different arrangements which are simply due to the molecule rotating as a whole or rotating about a particular bond. So here we have an example of butane, and we can see that it's not an isomer, it is simply rotated. Another important thing to remember is that when you have a single carbon-to-carbon bond, there is free rotation about that bond. So let's consider structural isomerism, and the two main types of structural isomerism are chain isomerism and position isomerism. So chain isomerism occurs because of the possibility of branching in the carbon chain. So for example, there are two isomers of butane. The molecular formula of butane is C4H10. In one of them, the carbon atoms lie in a straight chain, this, as you can see here, whereas in the other one, the chain is branched. So here we can see the two isomers of butane. So let's try naming these two isomers of butane. So for the first one here, we count that there are 1, 2, 3, 4 carbon atoms in the chain, therefore it is a but. And because there is only single bonds, it's an ane, so it's an alkane, so therefore this is butane. And for this isomer here, we need to count the longest carbon chain, so we have 1, 2, 3, therefore it's a prop. Again, because there's only single bonds here, the ending is ane, therefore it's propane. However, we have this group here, or the branch that happened, and it has one carbon, therefore we can use the prefix meth. But we also need to specify where the methyl group is attached, therefore we count onto which carbon the methyl group is attached, so we can see 1, 2, and even if we start from this side, is also 1, 2. Therefore, this isomer is called 2-methylpropane. Let's look at position isomerism, and the basic carbon skeleton remains unchanged, but any important or functional groups are moved around the skeleton. So for example, there are two structural isomers with the molecular formula of C3H7Br. I know we haven't encountered halogens yet, especially when they're attached to alkanes. This is quite a simple example to look at. So here, the bromine is attached onto the first carbon, therefore it is 1-bromopropane. In this isomer, the bromine is attached on the second carbon, therefore it's 2-bromopropane. And if we count the number of carbons in both of these, we get 3 carbons. So 1, 2, 3, and also 1, 2, 3. For the hydrogens, we have 3, 5, 7 hydrogens in this one, and we have 3, 4, 7 hydrogens here. And also we have 1 bromine here and 1 bromine here. Therefore, both of these have the same molecular formula, but as we can see, the bromine has moved on the chain. So these are structural isomers, in particular position isomers, because of the bromine moving around on the skeleton. Let's also briefly look at cycloalkanes. And cycloalkanes are simply carbon atoms that are joined together to form a ring. Therefore, when you see any of these drawings, you can add cyclo to the name to specify that the carbons are in a ring. So let's try naming these. So again, we count how many carbon atoms around the chain. So in this one we have 1, 2, 3. So it will be prop. Because there are only single bonds here, it will be propane. But because they are arranged in a ring structure, we add cyclo in front of the name. Therefore, this will be cyclopropane. If we try this one here, again, counting the number of carbon atoms, we have 1, 2, 3, 4. Therefore, it will be bute. Again, because there are only single bonds, it's a butane. And because it is arranged in a ring structure, this will be called cyclobutane. We can also try longer cycloalkanes by counting again the number of carbon atoms. We've got 1, 2, 3, 4, 5. Therefore it is pent. Only single bonds, meaning it's pentane. And because it is in a ring structure, it is called cyclopentane. And this final one here, we count how many carbons there are. 1, 2, 3, 4, 5, 6. Therefore it's hex. Because only single bonds, it is a hexane, and we add cyclo in front to show that the carbons are in a ring structure. Another thing to just be aware of is a general formula, which is CN2N. So this represents the general formula for cycloalkanes. Let's consider fractional distillation. And so we know that crude oil is a fossil fuel, and it's made from naturally decaying plants and animals that takes millions and millions of years. And crude oil contains different components that have different carbon chain length, weights, and boiling temperatures. So the first step is to separate these components. So because the different components have different boiling temperatures, they can be separated using this process called fractional distillation. So first of all, we have crude oil here, which is a mixture of different components. First of all, we need to heat the mixture to a very high temperature, and this is usually done with high pressure steam to temperatures of about 600 degrees Celsius. So then the mixture boils, forming a vapor or gas, and most substances will go into the vapor phase. So then the vapor will enter at the bottom of the long column, which is this, and it's called the fractional distillation column. And inside there are many trays or plates, and there is a temperature difference across the column, so you have hot at the bottom and cold at the top, or cool at the top. So then the vapor will rise in the column, and as the vapor rises through the trays in the column, it starts to cool. So when a substance in the vapor reaches a height where the temperature of the column is equal to that substance's boiling point, it will condense to form a liquid. So in this case, the substances with the lowest boiling point will condense at the highest point in the column, and the substances with higher boiling points will condense lower on. So as seen here. So at the top you've got gases which are relatively short. They only have about 4 carbons. And as you go down the carbon chain, so you have 80 carbons here in the chain. And then the trays collect the various liquid fractions. And then the collected liquid fractions will then pass on to a condenser, which then cools them further, and then they go into storage tanks. And from then on, they can, undergo further chemical processing. And this process is very, very useful for separating a mixture of substances with narrow differences in boiling points. So this is, a very important step in the refining process. And we can also see all the different fractions that come off. So we have gas at the top with a very short carbon chains, naphtha with 8 carbon, gasoline with 8 also, kerosene with 12, and so on. And they have very important commercial uses. So for example, petrol has anywhere between 5 to 10 carbon atoms, which can be used for car fuel. You also have diesel, which is between 16 to 30 carbons long, and that's used for larger vehicle fuels, just trucks and things like that. So this is just a brief overview of fractional distillation. So now we have considered fractional distillation. However, there is another process which is called cracking, which allows us to convert long chain hydrocarbons into valuable shorter chain hydrocarbons by breaking the carbon-carbon bond. So for example, once fractional distillation has happened, we can go further and convert the long chain hydrocarbons into valuable shorter chains, and this is done by a process called cracking. There are two types of cracking processes available. One is a catalytic cracking, where a catalyst is used, or thermal cracking. And this is very useful because it allows us to get shorter chain hydrocarbons, which are then used for cars. We use alkanes as fuels because they combust exothermically, so they release a lot of energy. So let's just look back at cracking quickly. So cracking involves breaking the C bond. So as I mentioned before, we're going from large hydrocarbons to smaller chain hydrocarbons. So in this case, we can see we have a 15 carbon chain, and through cracking we are able to get ethene, propene and octane. So we get one alkane and two alkenes, and alkenes we'll consider in a later video, but alkenes are hydrocarbons that contain double bonds. So catalytic cracking involves zeolites as a catalyst, and it's usually done at 500 degrees centigrade at a low pressure. We also have thermal cracking, which is done at a very high temperature, so 450 to 750 degrees centigrade, and the pressure up to 70 atmospheres. So let's look at combustion of alkanes. So combustion of alkanes generally destroys the whole molecule, and we use alkanes as fuels because when they combust, a lot of energy is released, so it's an exothermic process. Usually to achieve complete combustion we need excess air or oxygen, and the products are always water and carbon dioxide. So let's consider, for example, the combustion of propane. So it's C3H8 plus O2 gives us CO2 plus H2O. It's very important that we can balance this equation properly. So first of all, we need to consider carbons. On this side we have 3 carbons. On this side we have 1. So to balance them, we put a 3 here. Then we look at hydrogens. We have 8 hydrogens here and 2 here. So in order to get 8 on this side, we need to multiply this by 4. And the oxygens, we have 2 oxygens here. We have 2 times 3, 6, and 4, so 10 on this side. So in order to get 10 on this side, we need to put 5 in front of the oxygens. So that's now a balanced equation. An incomplete combustion happens, and this happens when there is not enough oxygen. So when the oxygen is not in excess, and this can lead to carbon or carbon monoxide forming. Carbon monoxide is a colorless and poisonous gas, and exposure to a very large quantity of carbon monoxide can lead to suffocation, because carbon monoxide binds to hemoglobin, which prevents oxygen from binding. And as we know, hemoglobin carries oxygen around the bodies. Therefore, if a lot of the hemoglobin molecules are taken up by the carbon monoxide, it can lead to suffocation. The reactions of alkanes with halogens, and this is also known as halogenation. So halogenation is where one or more of the hydrogen atoms in the alkane is replaced by the halogen, and halogens are fluorine, chlorine, bromine and iodine, and they are found in group 7 of the periodic table. Fluorine is the most reactive in group 7, and as you go down the group, the reactivity decreases. So alkanes reacting with fluorine, this reaction is very explosive, even in dark and cold conditions, so we won't consider it in much more detail. Alkanes reacting with iodine, under normal lab conditions, there is no reactions. The interesting reaction happened between alkanes and either bromine or chlorine. In the dark, no reaction will happen. However, in ultraviolet light or sunlight is present, a photochemical reaction will happen. So we will consider these in more detail. So, for example, let's take methane reacting with chlorine. This is known as free radical substitution, and we will discuss why this is called that. So first of all, there are 3 main steps in this reaction. So in the initiation stage, the chain is initiated by UV light, breaking a chlorine molecule into free radicals. And free radicals are reactive atoms or groups of atoms that have a single unpaired electron. So here we can see initiation. We've got chlorine and chlorine with a covalent bond. And under UV light, 2 chlorine radicals, free radicals, will form. And the way we know that this is a free radical is that we use this dot after the chlorine to show that this is a free radical. So, and this dot represents that this chlorine here has a single unpaired electron. So in the case of chlorine, this is also sometimes referred to as homolytic fission, and this is when free radicals form, the bond splits evenly, so each atom is getting one of the 2 electrons, like in the case of chlorine. So this is the initiation step. The second stage is propagation, and these are reactions which keep the chain going. So in this case, we have a methane and a chlorine free radical. Just a quick note on these curly arrows here, as you can see. I put a little side note here. So we use curly arrows to show the movement of electrons. When we have a full arrowhead, it shows the movement of an electron pair, meaning 2 electrons are moving. And when we use only 1/2 of the arrow, it means we are showing the movement of a single electron, like here. So the single electron here from the chlorine free radical will move in, and one of the electrons in this carbon-hydrogen bond will also move here, like represented here, to form HCl. And the second electron, which is between the carbon and the hydrogen, will move to the carbon, meaning that the carbon will become a free radical, and it shows that it has an unpaired electron. So another propagation reaction could be whereby this free radical here, so this unpaired electron would go here, and one of the electrons from the chlorine-chlorine bond will also go here to form chloromethane. and the other electron from this bond will go to the chlorine, producing a chlorine free radical. So as long as you're producing free radicals, the reaction will keep going. But let's consider what happens if no further free radicals are produced, and this is known as termination. In termination, reactions happen which remove free radicals from the system, and without replacing them by new ones, meaning that the chain cannot go on. Therefore, the reactions will terminate. So, for example, the termination step. There's quite a few possibilities, but some of the main ones are that two chlorine radicals will collide, forming the covalent chlorine 2 diatomic molecule, or you would have the methyl free radical colliding with a chlorine free radical, forming chloromethane, or you could have two of these colliding to form ethane. So this will terminate this reaction between methane and chlorine. Thank you very much for listening.